Hello again, Calculus 2 students. We're getting towards the end here. We're in 8.2, which has a bunch of different topics in it. So we're going to go back and forth with 8.2. But first we're going to talk about volumes of revolution. So last time we took the idea of slicing from area and we applied it to some general volumes. Here we're going to be focused on a bunch of different situations where we're doing volume of, we take curves on the XY axis and we're going to spin them and make disks. And we're going to get kind of some unique shapes. In fact, what I normally do for this lesson is pass around some manipulatives. So this is that shape. This is not supposed to be hollow like it is. It's supposed to be filled in. So pardon that. But the idea is that I have this curve which is square root of x, if I remember right. Yeah, and so if you take that curve and you put disks under it and you revolve basically the rectangles. Here, if you take those disks that you would get for integration and you spin them around the axis, you get disks. You add up all those disks, you get this picture. That's the idea of a volume of revolution. So we're going to take a curve on the XY axis. We're going to take its rectangles that you would use for integration and we're going to add them up. But first we're going to spin them around and make disks, then add those up. Okay, so going back to number one here, the idea of disks here. If I have a disk, skinny little disk with radius r and thickness h, it's going to be pi r squared h, which is, last time we used dh, but we're going to change that to dy here. So one of these, r is in the x direction, the thickness h is dy. That is going to be this one. Okay. The other one, r is measured in the y direction, and then h is dx. That's this curve, that picture. Okay, so this one over here, that's a dx picture. Okay, these are called parabolic solids, and then there's your generic math lingo about how it's very important to physics, blah, blah, blah. We're going to rotate the curve square root x to get this paraboloid, is what they're called. Okay, we're going to write x in terms of y, so x equals y squared, or y equals root x. We'll see which one we need. So this is the picture. We're going to add up the volume. Okay, so we need to get R. Think of each disk. This is, you might want to call it H, but it's the radius of the disk, right? And then DH, or DX, I should say, is the height of the disk, because the disks are sideways. So here, R in terms of Y is the Y value of the curve, which is square root X. Okay. So because this height, that's R, but it's the Y value is square root X. Adding up the, remember this is pi R squared when we did disks on the last lesson, times the thickness is dx. R squared is Y squared, which is equal to X, so pi X. And this curve is supposed to stop, they're supposed to tell you where to stop this one here, and they go farther than they should. We're just going to say, I want to say, yeah, I'm going to stop at 4 because that's where the last disk is. They should have been more clear, maybe stop the curve, but that's okay. So 0 to 4 for x, and you get pi x squared over 2, plug in 0 and 4. 0 won't matter here, you get pi times half of 16, which is 8 pi. Okay, so high five. There you go. All right. So let's keep going with this idea. We're going to spin a couple of different ways now. So this is a curve that actually the same curve, y equals root x. We're going to spin it now around the y-axis, and they haven't shown you the picture yet. But you can imagine making radius like this, or radii like this, and then spin them around like this and get kind of this funnel shape. In fact, I have a picture, or a manipulative here, that's same curve rotated around the other axis, looks like that. Okay, you can kind of see, you see all the circles that are inside there. In fact, there's not infinitely many, right? It's 3D printed and they use maybe a couple hundred or something. So you can see the circles on that shape. Okay. So we get a different shape now. I drew the solid, I drew a few sample disks. The radius of the disk, well, R is this way, right, which is now X. So in terms of x, it's x. In terms of y, it's y squared. So this is pi, and now the radius is y squared, so I should square that and get y to the fourth. This is a dy integral. This one is going to go all the way to the top of this picture, which is at 2. So 0 to 2 for y. Okay, and then I get pi y to the fifth over 5 for the antiderivative. 2 won't matter. 2 to the fifth is 32. And I got the right answer. Good! Okay, same curve, different vertical line. So here's the original curve here, minus 2. Okay, so the radius is now this long thing, and this long thing, and this long thing, and I'm going to spin that around. So this is going to be a wider funnel with a bottom that is a circle rather than coming to a point. Okay, so they already drew the discs. The center of the lines are at minus 2, and then the radius lies on the curve. What symbol gives us the thickness of these discs? Well, it's the same kind of picture as this one, so it's going to be a dy. Explain why the radius is 2 plus x. Okay, if we write it in terms of x. I'm going to explain that by talking to you. This distance right here, no matter how high you are, is 2 units. Down here it's 2 units, because it's just from minus 2 to 0. Okay, so that's always 2. This length is the x value of the curve at each point. Right? That's exactly what we did over here. We said the radius was x. This is x, but then 2 more. So no matter what, this is 2 plus x. That's very hard to wrap your head around and easy to get backwards, and we'll do some others where you have subtraction. It's very convoluted, and I always have to think about it twice. So please ask me questions if you get stuck on that part of the homework. Okay, so the radius then is 2 plus x, but remember that x equals y squared, so 2 plus y squared. And so this is going to be pi 2 plus y squared, quantity squared, dy, and then 0 to 2 again. Okay, so you're going to think about this integral and how to do it. Don't make it harder than it is. You just FOIL it. I'm not going to do the whole thing out. You got the answer there, but I want to show you the trick. So remember that fancy algebra is also a technique. So this should be 4 plus 2y squared plus y to the fourth. I pulled the pi out. Now you can use the power rule. So pi, 4y, 2y cubed over 3, y to the fifth over 5, plug in 0 and 2. You do all that, you can check me, you should get that answer there. So don't forget about foiling. The hardest part of this problem, I'm not really going to make you do these integrals out for this. It's more about setting up the integrals. But getting to that point and doing it right can be pretty difficult. So that, when I just circled there, that's the tough part. That's the important part. Okay, so let's do one more example with a different curve. This is going to be cosine x. So I'm going to try to draw it here. It starts at 1. And this cosine of pi over 2 is 0. Pi over 2 is 1.4-ish something. And then it goes down to minus 1. It gets to minus 1 what at pi, so I'm going not very well. Something like this, right? And then here's y equals 1. And I can draw. Wow, that's really bad. Little laugh for you guys. So y equals 1 should be here. And then those were supposed to touch at 2 pi. So pretend it's over here. Again, this is why I don't teach Calc 3, people. Okay, so those are the curves they told me to draw. X equals 0, x equals 2 pi. And we're going to rotate around this. So this stuff, rotated around here, would make kind of a bell shape with points on the end. Okay. Draw one small vertical disk whose center is on the line and whose radius is on the line cosine x. So they're talking about this thing. Okay. And how long is the radius of that? Okay, focus over here for a minute. This would be the y value of the curve. And so the thickness here would be dx. So this is going to be dx. But for the radius of the disk, the y value is under it. And the y value plus the r, y plus the radius should equal 1, right? Because you're going up to 1. So the radius is going to be 1 minus y. Now over here that might seem confusing, but it's not, because here's 1, here's the y value, but the y value is negative, so subtracting the y value makes it bigger, and that's why these are longer. So that does work. And of course y is cosine x. So like I said, last time we added, this time we subtracted. That's very easy to get backwards. Please ask if you get stuck on those ideas. Okay. So let's draw the solid you get. I already did that sort of. Set up the integral. That's going to be pi 1 minus cosine x squared dx, and 0 to 2 pi. Use some algebra. So same idea as before with the other integral. We're going to multiply this out. 2 cosine x plus cosine squared x. You should know how to integrate cosine squared x because we did it on our gateway. But they give you a nice little fact at the bottom that becomes pi. So that would be x minus 2 sine x. Evaluate 0 to 2 pi. Pi times this. And they already told you that the other part is going to be pi out from the outside, and then pi was the answer they told us. So pi, 2 pi, minus 0, and then 0 minus 0 here, plus pi squared. So convoluted way to say 2 pi squared plus pi squared is 3 pi squared, which is what they said the answer was. Like I said, I'm not so concerned about doing the integrals out. I'm concerned that you can set this up. That's the hard part. Make that 2 more clear. So when you're doing these volumes of revolution, figure out where the axes and what is the radius. That's the hardest part. Is it dx or is it dy? Where's the axis of rotation? That kind of stuff. So please ask if you get stuck on these.